A pan balance, shown here, is a device for measuring mass. The way it works is that there is a known quantity of mass on one side of the pan balance and an unknown mass on the other side. If the two masses differ, the beam will rotate about the pivot. If this side is heavier, for example, this side will go down and it will push the other side up. When the masses are equal, the pans will balance out, and you'll know how much unknown mass you have by how much known mass it takes to balance it out. But because we're looking at the masses here, this instrument does not depend on the strength of gravity, because whatever gravity is acting on one side is acting on the other side in equal measure. So what we're focusing on is the actual mass of the object, which is a measure of the object's inertia, the object's resistance to motion. Another way of thinking about that is mass is the amount of matter in an object, how much stuff is in that object, and is an intrinsic property of an object. It exists as part of the fundamental makeup of that object, and if that object is moved from Earth to the Moon or Mars or space, the mass of an object will stay constant. Gravity is an attractive long-range force between two objects that depends on the mass of those objects. If you have two objects with masses m1 and m2 that are separated by a distance r, those objects are going to feel a gravitational force equal to capital G times the masses of the two objects divided by the distance between their centers squared. This is a foreshadowing of Newton's third law, the equal and opposite reaction, which tells us that the force that the first object puts on the second object is equal to the force that the second object exerts on the first object. One thing to note is that for capital G, the universal gravitational constant, it has an order of magnitude of 10 to the negative 11. So the capital G in this gravity equation is very, very small. And so we see that we'll only see a significant force when the masses are very big to make up for this very small amount in capital G. The gravitational force between human-sized objects is very small. As we just mentioned, humans are on the order of magnitude of tens to maybe a couple hundred kilograms, and the universal gravitational constant has an order of magnitude of 10 to the negative 11. So objects with small mass will feel a very small gravitational force, a negligible or unnoticeable gravitational force. But when we talk about planet-sized objects, when you have very, very large masses, then gravity can become a significant force. And that's actually what happens when we talk about gravity pulling us down. If you have an object near the Earth's surface, since we're on a space frame that's much, much smaller in terms of height above the Earth's surface compared to the actual radius of the Earth, we can treat the ground as being flat, even though we know that in fact there's a slight curvature to it. And basically what's happening is the mass of the object and the mass of the Earth are pulling each other together over this distance of the radius of the Earth. And so for objects that are near or on the surface of a planet, the force of gravity is that gravitational attraction, which is the universal gravitational constant times the masses of the two objects in question. In this case, capital M is the mass of the Earth and little m is the mass of the object, divided by r squared. And so this is the gravitational attraction between two objects. And then when we talk about the weight of an object, the force downward, the gravitational force on an object, that gets down to mg, which is what we're used to seeing. Another way to look at gravity is to imagine a person standing on top of the Earth. And so here is the Earth. We have oceans. We have land. More oceans and more land. And so what happens is all of the mass in the person is attracting all of the mass in the earth. And so some of the mass right next to the person is very, very close. And so in that case, when we're looking at our force, the distance between the mass of the person and the mass of this part of the mass of the earth is very small. And so the distance between them is small, but we're also talking about a small overall contribution of the mass of the earth. To treat the whole mass of the earth, some of which is very close to the person, but some of which is very far from the person, what we can do is actually treat the whole world like a point mass. And so when you have an approximately uniform mass like you have in the earth, instead of treating it in 3 dimensions like a sphere, you can treat it as a point mass with all of the mass of the earth concentrated at this point at the center of the earth. This approximation only works as long as you're outside of the earth, but all of us living on earth are outside of the earth. If you were to go inside, then the approximation breaks down, and you'd have to look at a different situation. But this trick is used commonly in electromagnetics as well. And so if we consider, again, our person standing on the earth, instead of dealing with a complicated distribution of mass, we have one person who has one center of mass to them, and they are one distance in an Earth radius from this concentration of mass of the Earth. And so in that situation, you have the force of gravity, which is depends on the mass of the person and the mass of the Earth, and that person is thought to be an Earth radius squared away from where all of that mass of the Earth exists. And that force of gravity is what we feel as weight. It's the mass of the person times our acceleration due to gravity. And we see that those cancel out. And thus we have an equation for gravity. It's the universal gravitational constant times the mass of the Earth divided by the radius of the Earth. The universal gravitational constant is 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the 24 kilograms. And the radius of the Earth is 6,371 kilometers. And so we'll write that as times 10 to the 3 meters. And when we plug in all of these numbers, we find that the planet Earth should give us an acceleration of 9.810360 on and on. Because of sig figs, and because of the nature of the number where it gets quite small pretty quickly, that's where we get this value for the acceleration due to gravity. We just used the magnitude of the gravitational force to find that the acceleration due to gravity depends only on the universal gravitational constant, the mass of the planet, and the radius of the planet. And so we see that the gravitational force and the gravitational acceleration don't depend at all on the mass of the object in question, since the mass of the object cancels out. We also see that for any given planet with a specific mass and radius ought to have a constant value for gravitational acceleration. We've talked about free fall in previous modules. We're talking about an object that's falling near the surface of a planet. And so in that situation, the net force on the object is only the gravitational force. And the acceleration free fall should be the force of gravity divided by the mass of the object, which we've seen cancels out to be g. And thus, for any objects on the same planet, regardless of the masses of those objects will have the same free fall acceleration. On a different planet with a different mass and radius, there would be a different fixed value of the gravitational acceleration, but then all objects on that second planet would all have the same gravitational acceleration. When you weigh yourself, you stand on a spring scale, and you are compressing the spring in that scale. And then when you come to equilibrium, the scale knows how much force you're applying to it by how much upward force the spring has to exert to hold you up. And so the weight that we're talking about, when we talk about the weight of an object, would be the reading of that scale when the object is at rest relative to the scale. And so we're talking here about weight as a measurement. It's a measure of how much force is needed to hold up an object. Here, the force of the spring is that force, and thus weight should be measured in newtons. Weight is a force as well. And the weight can also be thought of as the normal force required to hold up an object in a given situation. So when you stand on a spring, you have a force of gravity that is pulling you downwards. But if you are at rest, if you are in equilibrium, then the net force has to be zero, which means that there has to be an upward force pushing on you. There has to be a normal force keeping you from falling through the scale and through the ground. The springs in the scale provide that normal force to hold you up, and the scale is calibrated to measure how far you've compressed the springs, which tell you how much force is acting on those springs. And from there, it can calculate mechanically what your force of gravity must be that you're applying, and thus what your weight would have to be. So in this situation, as long as you're at rest relative to the scale, the force that the springs are reading has to be the same as the force of gravity, which is your mass times acceleration. Typically, when you're measuring your mass or your weight in, you'll measure your weight in kilograms, which is a bit of a misnomer, because what's actually happening is it's measuring your gravitational force, and then it's dividing out the factor of g to give you your mass in kilograms. Before we were talking about weighing yourself when you are at rest, and in that situation, the sum of the forces is equal to zero. And that was how we got to the fact that the force that the spring is exerting to hold you up, which is the normal force in that situation, is just the force of gravity of you pushing down on it. However, if we consider instead a situation where we are accelerating upward in an elevator while weighing ourselves, in that case, the net force is the force of the spring and the force of gravity. The spring is pushing us upwards, and gravity is pushing us downwards. But there's a net upward acceleration. And what this means is that the force of the spring, the normal force of the spring pushing us upward, has to not only balance out gravity, but the force of the spring has to be greater in order to cancel out gravity and have value left to push us upwards. And so if we're reading the scale, and the scale is giving us a number based on the force applied to the springs, then we can see that if we're focusing on the force of the spring, we can move gravity over, which gives us this relationship, where the force of the spring is the weight, or the gravitational force on the person, plus the component for the upward acceleration. And we see that the weight of the person or of the object would be mg plus, or mg times 1 plus the acceleration in the y direction divided by gravity. And so in this situation, if the acceleration upwards is a positive number, that means that this is greater than 1, and your scale reading is larger, meaning you're heavier, you weigh more as the elevator accelerates upward. You notice this through the normal force, through what you feel in your body. So if you are accelerating upward, you feel heavier. That heaviness that you're feeling is the increased normal force pushing you up, balancing gravity, but also accelerating you upward. If the acceleration is negative, that means that you're on an elevator that's going upwards and you slow down to stop at a floor, for example. That means that if the acceleration is negative, this number is less than 0 and your weight is less than it normally is. And that means that you feel much lighter than you normally do, and you will know that feeling as well when you are going upward in an elevator and stop. You feel like you're floating for a second. However, these only work, this effect is only true while you're accelerating. If you're moving at a constant velocity, the acceleration is 0 and there's no extra force needed to keep you moving upward at a constant velocity. And so then there's no change to your weight in that situation. We just saw that the weight of an object measured by the normal force required to hold that object up is not always equal to the gravitational force. But if the object is accelerating upwards and the acceleration in the y direction is positive, then the weight will be greater than normal. And if the acceleration is negative, the weight will be less than normal. In that situation, taking that to an extreme, we can see that if the acceleration downwards is negative g, then this whole term goes to 0, and the weight goes to 0. And so an object in free fall has no weight. And that's something that they can do in NASA, where they have a plane that will fly way up in the air, and then it will dive down, and it will accelerate downwards at exactly 9.8 meters per second squared, and everybody inside feels weightless and floats around for a few minutes. We also know that astronauts float around and are weightless while they're orbiting the Earth. And the question, does this mean that they're in free fall? Yes, it does. That's part of the orbit, means that they are always falling downwards due to gravity, but part of being in orbit is that they're flying forward so fast that they never actually fall straight down to the Earth. They always fall around the Earth, and that's how they continue to orbit for months and years at a time.